For me at least, solving a sine or a cosine equation is a lot easier than solving a tangent equation just when it comes to just thinking about the unit circle. So when I look at this problem, I know that cotangent is undefined when its denominator is equal to 0. So we know that the asymptotes occur when this denominator is equal to 0. And so this becomes an equation that I just want to solve. So I can find my asymptotes by taking this sine equation and setting it equal to 0. And so to solve this equation, there are different routes you can take. I know for those of you who had me last year in pre-calculus, these are ones that I called like the smiley face problem, the very mathematical, but not really mathematical sounding types. Those of you coming from Mr. Burton's class or Ms. Rivera's class, I'm not quite sure how they showed you to solve it, but you do just need to be able to solve these problems. The way that I solve them is I think of this as this 5x minus pi over 3 is all inside of the function, so you can't really touch it right now. So in my head, I just think of this as the sine of something is equal to 0. And there's why I call it the smiley face problem. And so think to your unit circle, where is sine equal to 0? Sine is equal to 0 at 0. Sine is equal to 0 at pi. So again, we have the unit circle. It's equal to 0 at pi and 0. We need that reminder. Also 2 pi, but we do know 0 is the same thing as 2 pi. That would be your answer, but that's not what was on the inside. The inside was this 5x minus pi over 3. And so there, after I figure out what sine was equal to 0, I want to finish solving this equation. So like the first one, I can go ahead and add the pi over 3. Second one, I can also go ahead and add the pi over 3. I'm going to think of that as a common denominator, and it gives me 5 pi. I don't know where I got the 4's from. Let me try that again. Get my common denominator of 3 pi over 3. Here's where the 4's coming into play. So add pi over 3, and I get 4 pi over 3. And then I want to divide by 5. Remember, dividing by 5 is the same thing as multiplying by 1/5. So I have one vertical asymptote at pi over 15 and another vertical asymptote at 4 pi over 15. And so those are two equations of your vertical asymptotes. So we know that we do have a non-removable discontinuity at x is equal to pi over 15 and x is equal to 4 pi over 15. You might ask yourself, well, how do we know it's non-removable? We know it's non-removable because we have those prereq skills. We know that cotangent has vertical asymptotes, and vertical asymptotes are going to be non-removable. Now, these are only two of them. So I do also just want to remind us of some other things with trig. This cotangent function, let me just remind ourselves what it looks like if you need that reminder. The cotangent graph, remember, looks like a bunch of decreasing kind of cubic functions. And it just kind of repeats that forever and ever and ever. So we have these asymptotes that keep repeating. So when I say I have a non-removable discontinuity at pi over 15 and 4 pi over 15, that's technically just two of an infinite number of asymptotes. Does anyone remember thinking back, this is all the way back to unit 2 of pre-calculus, does anyone figure out how we can figure out how often those asymptotes are going to be repeated? Well, if you don't remember, it is the period of the graph. We know that for trig functions, they are called periodic. That is meaning they repeat over and over again. For sine functions, cosine functions, and their reciprocals, the formula to find the period is 2 pi over b. for tangent and its reciprocal, its formula is just pi over b. So the equation that we solved in this one, these were a sine equation. Like I know that the original one was cotangent, but this is a sine equation. And the b value is that 5. So like this may not concern most of you, and I don't know if this is going to go over a lot of heads or not. But one way to show all the asymptotes is these are going to repeat every 2 pi over 5, and I use the letter n. And this is going over your head right now. That's kind of okay. I mainly just want us to understand where I got the pi over 15 and 4 pi over 15 from. But for those of you who are ready and kind of why it makes sense, every time you go over by 2 pi over 5, you're going to hit another asymptote. But for this class and for right now, I'm most concerned that you can find at least 2 of those vertical asymptotes.
Why would it be 2 pi over 5 instead of just pi over 5?
Good question. So the short answer, the equation that I solved, and I'm actually going to show you several ways to write this. The equation that was being solved was a sine equation. So that's where I was using the period formula from, since this was sine. Another way to write these answers, I can actually combine those answers. And I'm just going to pick the smallest one. And I have plus, and since the original one was a cotangent, I can use the tangent formula. So I can write it as pi over the 5n. And that answer I wrote in red includes all of those together. So that's kind of where the period of cotangent is coming. And that's just because it might help if I get like a common denominator here. That becomes 3 pi over 15n, not an extra pi there, but over n. And some of you, like you can kind of see, if you start with pi over 15, if you keep adding this 3 pi over 15, like you'll get the 4 pi over 15, and then you'll just keep getting every single asymptote after it. So you can just use the pi over 5, and you would actually have the same answers. And that's probably even the shortest way to write an equation for all the asymptotes. Basically, every time you go over by pi over 5, you hit another vertical asymptote. Did that make sense?
Yes, thank you.
You're welcome. And I honestly don't care. I just want you at this point in Calc AB to know how to find at least 2 vertical asymptotes of our trig functions that have vertical asymptotes. Other types of problems that have discontinuities are going to be weird ones like this. I'm trying to just expose you to a variety of problems. I got a lot of these from like old AP questions. And it says discuss the continuity of the function. And so normally we're used to seeing things like x minus 4 over x squared minus 16. But this has the absolute value of x minus 4, so we do need to think about it a little bit differently. So the first question I want to ask you is how can we go about figuring out where this function would be not continuous at? Where do we find points of discontinuity?
The denominator.
The denominator. So let's go ahead and we can factor the denominator. And I have x minus 4 and x plus 4. So looking at this, we do have points of discontinuity, so I can say it's continuous everywhere, except x cannot be equal to 4 and x cannot be equal to negative 4. And we know that we can classify these as non-removable and removable. And I chose this one because it's kind of going to be a weird case. So let's do the easier one first. We see we have this x plus 4 right here. There's no way it can cancel out. That factor did give me x is equal to negative 4. Since it doesn't cancel out, what type of discontinuity do we have there?
Non-removable.
Non-removable. And if it doesn't cancel, we know it's non-removable because it is a vertical asymptote. So now this other one that does give me x is equal to positive 4, if, and that's a big if those absolute value bars were not there, that x minus 4 over x minus 4 would cancel, and we would have a hole. What's kind of weird in this one is when you have the absolute value there, like you can't cancel the x minus 4s because even though they're the same, one of them is kind of stuck inside an absolute value. If you're just okay with memorizing something, then you can make a note of this, that whenever you cancel two factors and one of them is an absolute value and the other one's not, that is no longer a hole, but it's going to end up being a jump. So if you are okay with just memorizing that, then you just know that x is equal to 4 is a jump. I do think it's important though to kind of see why it's a jump. And also I know a lot of people, they do honestly care why it's a jump because it helps them remember it if they know kind of where and why it comes from or why it is the way it is. And the reason why it ends up being a jump is I'm going to just think about some limits. I'm going to kind of write out to the side. I'm going to have the limit as x goes to positive 4 of this function. And I'm going to go ahead and leave it factored. And I'm going to think about it as again as x goes to 4. And I'm going to write it twice because if this is a jump, then if I come in from the left-hand side, I should get one number. And if I come in from the right-hand side, I should end up getting another number. So how we can think about why this is a jump, and I just want to kind of help, this is also just a good review of some intuitive limits. If I'm coming in as x goes to 4 from the left, what's a number that's like immediately to the left of 4 that I can think of in my head to help me think about this problem?
3.
3, let's get even closer to 4. So let's just do like 3.9. But again, we're just kind of thinking about this in our head. We're not really going to use it to solve the problem. But 3.9 is like immediately to the left of 4. So when I look at this problem and I'm just thinking about plugging in 3.9, and again, that we're not really plugging in 3.9, we're plugging in 3.9 that's going to immediately change into the number 4. So in the numerator, I have 3.9 minus 4, which is like negative 0.1. But since that numerator is in the absolute value, we know that the sign of it is always going to end up being what?
Positive.
Positive. So we know that this numerator, like whatever it is going to end up being positive. But I have this same factor, which would cancel with it. But if I have 3.9, so something to the immediate left of x minus 4, is it going to end up being positive or negative? So 3.9 minus 4 in the denominator would end up being negative.
Negative.
And so the answer that we have, so I'm going to pretend like those are canceling right now. So we do have a 1 left over in the numerator. I can go ahead and do my direct substitution. 4 plus 4 gives me 8. But when I canceled, I had 1 was positive and 1 was negative. So it's not going to end up being positive 1/8. It's going to end up being negative 1/8. And then I can kind of repeat that process for that other one. So I'm going to think about something to the right of 4. So I'm going to think of something in my head like 4.1. So in this one, the numerator is still always positive. Well, now something to the right of 4 minus 4 is going to end up being positive. So when those cancel, that's fine. I still have 4 plus 4, which is 8. But since this one was a positive over a positive, we end up having a positive 8. So again, the short answer to this, if you just want to know that when you cancel out two factors and one is an absolute value and one is not, it's going to be a jump, basically because one's going to be a positive number, the other one's going to be negative. That's fine by me, and that's really all you need to know. If it helps for you to see why it's a jump, then that's what that work on the right side of your notes is kind of coming from. Any questions on that one?
No.
All right, so I actually just have one more problem for us to do, and then that's going to be the end of today's notes. So this one, instead of discussing the continuity, I did want to kind of change it up a little bit. I do have another one like this, but I'm going to save it as a warm-up for after the long weekend to see how much we remember / forget. But when you're looking at this one, I have find the value of b that would make f continuous for all real numbers. And so I have this piecewise function. I have one piece that's happening when x is less than 5, and then I have another piece that is existing when x is greater than or equal to 5. And I need to figure out what this b value is to make this function continuous. So to give you a visual what's happening in this, like I'm not going to graph the actual function, but basically we have some graph that looks like something. 5 is some sort of boundary point. To the left of 5, we have this like rational square root function, and it's coming down, and it doesn't include 5. And for this second piece, we are looking for a graph so that when it starts where 5 is equal to, it doesn't start like above here, it doesn't start down here. We want to fill in that hole and then continue so that they are connected and that your function is continuous. So if I want to figure out a way to make our function continuous, any ideas of what you could do for this problem?
Plug in 5 to the top.
So we can plug in 5 to the top and see what we get. So plugging 5 into the top, I have 2 minus the square root of 5 minus 1 all over 5 minus 5. And that's going to give me 2 minus the square root of 4, which is 0. And then we get 5 minus 5, which is 0. And then we're like, oh crap, because we get 0 over 0. So what does that mean we're probably actually going to have to do for this problem?
Rationalize.
Rationalize. So some people are like, okay, so I just need to rationalize and plug in 5. The calculus fact we're actually using here is that for a function to be continuous, the limit has to exist. If the limit is going to exist, then we know that the limit on the left-hand side and on the right-hand side of the function must exist. So my setup for this question is I want to find the limit as x goes to 5 from the left of f of x. And if it's continuous, that needs to be equal to what's happening as x goes to 5 on the right-hand side of that function. The easy part of this is we can do the right-hand side, because that's just going to be the limit as x goes to this 2x plus b. And I can go ahead and do my direct substitution. 2 times 5 plus b are 10 plus b. The other side is where I think it was Gautam who said it. We need to rationalize, then plug in the 5, and then we have our equation that we can solve. I'm going to kind of rationalize out to the side just because there's a lot of work going on in this problem. It will let me. So I have this 2 minus the square root of x minus 1 over x minus 5. So we know when we rationalize, we multiply by the conjugate of the part that has the square root sign in it. And so my numerator, I have 2 times 2, which is 4, inner outer cancel, minus x minus 1, all over x minus 5 times 2 plus the square root of x minus 1. And then simplifying this, I'm going to go back and squeeze it down here. So I have 4 minus x plus 1, so that's going to be a 5 minus x over x minus 5 times this portion. And we look at this, we're a little bit sad because nothing is canceling quite out yet, but we do see things that are very similar, so good review here. What can I do in that numerator so that I can end up canceling something out?
Factor out a negative.
Factor out the negative. So we have the limit As x goes to 5 from the left, by pulling out a -1, it now works. That cancels, and now I can go ahead and plug in that 5. So I have -1 over 2 plus the square root of 4. I erased it, so I'm going to rewrite it up here. 2 times 5 plus b, 10 plus b. So solving this equation, we have b is equal to this -1 over 2 plus the square root of 4 minus 10. Again, I am perfectly okay with ugly answers. I know most of you hate ugly answers like that, but we can leave our answer like that. If you really don't like it, then we have like -10 minus another -1/4. And that's the same as saying -10.25 as well. So again, what did we basically do here? I want to make sure the calculus content makes sense. We know that if this function needs to be continuous, that when you come in from the left-hand side and when you come in from the right-hand side, it has to match up. Well, what does it really mean when we say come in from the left and come in from the right? We're basically saying that the limit on either side of this graph has to work. Many of you probably could have done that by showing a whole lot less work. But the main idea here is we know that we want to set the two pieces equal to each other at the x value of 5. Any questions or things that I can clarify about that problem for you?
Yeah, I got a question
Go
about
ahead, Mitch.
the -10.25. Did you just solve further?
Yeah, that was me just simplifying it because this part becomes a -1/4 minus 10. And that's where that was coming from.
Okay.
But again, you're welcome, and that's why I kind of put the ugly answer in a box. Because like on my test, if you stop there and box your answer, that would receive full credit. If you try to simplify it further and say you accidentally simplify it incorrectly, then you lose a point. And the AP exam grades it the same way. Any answer that's as long as it's an equivalent numerical value would receive full credit. And it just saves a whole bunch of time to just leave it ugly as long as you're okay with answers that look like that. Any other clarifying questions?
Mr. Brown,
Yes.
if there were could there be more parts to that, than 3? Or than 2, sorry.
Yes, so we did see this piecewise function we did yesterday that had 4 pieces. And I do have a warm-up. I'm saving it for next week as part of our test review. But I do have a warm-up that has a and B variable you solve for. But the process is still basically the same. You end up just still setting equal to each other, the parts that are next to each other. So in this one, there's just 2, so we set them equal. But if I have, I'm not gonna make one up now, but if I have 3 parts and it's something like, you know, 3 parts like that, then I would still set, you know, the first 2 equal to each other and then the last 2 equal to each other and set the limit, one's gonna have a limit at 2, the other ones have a limit at 0.
Okay.
So I can make them longer, but the idea is still gonna be the same where we're still setting the left and right hand side of a number equal to each other. So your homework, again, I do want you to enjoy your long weekend. I think you deserve it. Your test is next week. And the homework I'm really only assigning is this homework 4 and homework 5. We have the limits intuitively and then the limits and continuity. They are due on the day of your test, which is going to be on Friday. And then if you really want to get ahead, you can work on your briefcase binder, which has been distributed out to you. But again, we have 3 days of review next week, which honestly is probably too many review days again, but I am fine with making sure you feel comfortable with this first test grade that you have for my class. Remember, if you do all of your homework and your test grade ends up being higher than your quiz grade, then I would replace your quiz grade completely with your test grade. Other than that, that's it for today's class. So I guess you have 10 minutes to work on homework or 10 minutes to start your weekend early. Do enjoy your weekend though. I am serious about that. Spend some time not looking at a computer screen and not thinking about school. And I will see y'all on Tuesday. Mitchell, you're raising your hand. What's up?
Yeah, I have a